Hello everyone, in today's lecture we will continue working with the Z transform, and in the previous few lectures we have talked about the definition of Z transform, how to compute the region of convergence, how to find the inverse Z transform, and the properties of Z transform. And in today's lecture we are going to use all what we have learned so far to apply it to LTI systems, linear time invariant systems. If you remember from the introduction we had and from the signals and systems course, LTI systems are completely characterized in time domain by what's called the impulse response h of n. And by completely characterized we mean that we can get the system properties from the impulse response like causality and stability, and knowing the impulse response h of n, we can compute the output of the system y of n given any input x of n. That's why we say h of n provide a complete characterization of the system at hand. We can use the convolution property of the Z transform to write down y of z, the output in the z domain, that would be equal to x of z, z transform of the input multiplied by h of z, and h of z is the z transform of h of n, and it's also called the system transfer function or system function. So h of z is a system function or system transfer function. Using this property we can find that h of z equals y of z over x of z. So now, knowing the input x and the output y, we can get h of z, system transfer function, by dividing y of z over x of z. Example. Let's say we have an LTI system whose impulse response is a to the power n u of n. And the input signal to this system is u of n. And let's try to find the output signal y of n. In other words, I can ask you to find the step response of the system, because the input x of n here is the unit step. So I can equivalently ask you to find the step response of the system. Of course, since it's an LTI system, the output y of n would be the convolution between x of n and h of n. So this problem actually can be solved in two approaches. The first approach is to do the convolution in time domain between h of n and x of n, and I will leave this to you as an exercise. And the second approach is to use the Z transform, as we are going to see in a few seconds. So let's move to our whiteboard over here. So we have a system whose impulse response h of n equals a to the power n u of n, and the input is x of n. So in order to compute the output, we simply write down that y of n is equal to x of n convolution with the impulse response h of n. And then we use the Z transform property, which says linear convolution in time is a multiplication in Z domain, so y of z equals x of z times h of z. So what is the Z transform of h of n? It's h of z, which is basically 1 over 1 minus a times z minus 1, and the ROC is modulus z larger than modulus a. This is basically what we have learned from the previous few lectures, how to compute the transform of a to the power n u of n. And for u of n, it would be 1 over 1 minus z minus 1. It's similar to h of n, except that a is equal to 1 right now. So moving on, so y of z would be equal to 1 over 1 minus a z minus 1 times 1 over 1 minus z minus 1. And here this is Z transform of U of n. And now these two are multiplied together. So in order to find y of n, we need to do inverse Z transform. So we are going to do partial fraction. Why is that? Because y of z here is a rational function. It's ratio between two polynomials. Here in the numerator, polynomial of order 0, there is no z. And in the denominator, we have polynomial of order 2. So it's a proper rational function. And we can simply write it as a constant over 1 minus a z minus 1 plus another constant b over 1 minus z minus 1. And of course we can easily find the constants a and b. Now what about the region of convergence? Of course the region of convergence has to be the intersection of this ROC and the ROC of this term. The ROC of this term is modulus z larger than modulus a, and here modulus z larger than 1. So the ROC should be the intersection of these two. So it would be like this. This is the Z domain, and this is a unit circle, a circle with radius 1. So the ROC is either larger than 1 or larger than modulus A. If you go back to our problem statement, we can see that modulus A is less than 1. So let me draw another circle inside the unit circle whose radius is modulus A, because it's less than 1. And now the ROC should be the intersection. So the ROC is either larger than modulus A or larger than modulus 1. So the intersection in this case would be modulus Z larger than 1. That's why we can find the Z transform to be a right-sided sequence because the ROC is larger than 1. So y of n would be, if we move back over here, so we have a constant a over 1 minus az minus 1. In this case we have a term in time domain that will take this form. A times a to the power n u of n, and the other term is 1 to the power n u of n, and this would be the output from the system, or the step response in this case. Of course, computing a and b is no big deal. We have done this multiple times before. Let me remind you of how to do it. We would basically say that a times 1 minus z minus 1 plus b times 1 minus az minus 1 equals 1. So let me solve it in details on our whiteboard. So in order to find the constants, we'll have 1 would be equal to a times 1 minus z minus 1 plus b times 1 minus a z minus 1. So if we put z equals to 1, which is the pool in this term, we will get the following. So 1 equals to, the first term would be 0. If you put here z equals 1, this term will cancel out, it will be 0, plus b times 1 minus a small, which means that b would be equal to 1 over 1 minus a. Similarly, if you put z equal to a, this term will cancel out and you will get a would be equal to another equation. So let's go back to our slides over here. So solving this example, we find first h of z to be 1 over 1 minus az minus 1. and x of z to be 1 over 1 minus z minus 1, and then y of z is a multiplication of the two. And here we're using the convolution property, which says convolution in time is multiplication in z domain. And then we would choose the ROC to be the intersection of the two ROCs over here, either modulus z larger than modulus a or larger than 1, and here we get the maximum, of course, 1, or modulus a, which is 1, as we have seen on the whiteboard. Now using partial fraction, and we'll get a and b as we have discussed on the whiteboard. And now we have our step response, or the corresponding output. It's a constant a times u of n and a constant b times a to the power n u of n. Okay, so now let's go back and talk about the properties of the LTI systems and how they are related to the impulse response of the system. As you remember, for a causal LTI system, the impulse response h of n should be 0 for n less than 0. This was the condition for causality and its relation to the impulse response. So the impulse response must be a right-sided sequence. If h of n is a right-sided sequence, this means that its region of convergence must be going outward. Hence, the ROC extends outside a circle of some radius r extending to infinity. So now we are relating what we know about causality and how the impulse response for a causal system should look like to the region of convergence and Z transform. But this condition, which is that the ROC should be going outward for a system to be causal, is a necessary but not sufficient condition. How is that? Because remember also that h of z is a summation from minus infinity to plus infinity h of n times z to the power minus n. And if h of n is 0 for n less than 0, then the summation should start from 0 over here. Which means that h of z does not include any positive power of z. If you expand the summation, it's h of n z to the power 0 plus h of n z to the power minus 1 plus h of 2 z to the power minus 2 and so on. All we have is negative powers of z. If we do not have any positive power of z, this is a causal system. So the causality here has two-fold condition. The first one is ROC extending outside of a circuit, going outward, and also h of z should not have any positive powers of z. Okay, the stability. As we have seen in the introductory part of this course, for an LTI system to be stable, h of n must be absolutely summable. That is, summation of absolute value of h of n from minus infinity to positive infinity should be less than infinity. In this case, h of z can actually be related somehow to this definition. How is that? So, h of z equals summation from minus infinity to infinity h of n z to the minus n. If you take a closer look, this summation is similar to this summation except for a few differences. First, it's from minus infinity to positive infinity, same here, h of n. But here we have modulus h of n, and we do not have this z. So, what if we take the absolute value of h of z? Absolute value of h of z would be equal to absolute value of the summation, which is less than or equal to summation of the absolute values. So summation minus infinity to positive infinity, modulus h of n, modulus z to the negative n. Now, what would happen if we put z, modulus z, to be equal to 1? In this case, if modulus z is equal to 1, as if we are calculating the values on the unit circle, modulus z equals to 1 is the unit circle. In this case, putting modulus z equal to 1, so we'll have 1 to the power minus n, which is always equal to 1. And now h of z evaluated at the unit circle will be this summation, which is a summation of stability. That's why if the system is stable, modulus h of z at modulus z equal to 1 is less than or equal to this summation, and this summation is a summation for checking the stability, this one over here. So if the system is stable, then this summation is less than infinity, then h of z at the unit circle must be less than infinity as well. And what does this supposed to mean? It means that the values of h of z evaluated at the unit circle has to be less than infinity. In other words, the unit circle must be part of the region of convergence, because we know in the region of convergence the values never go to infinity. So again, this equation means that on the unit circle, the system has finite values of h of z. In other words, the unit circle belongs to the region of convergence. Okay. Therefore, an LTI system is stable if and only if the region of convergence of the function h of z includes the unit circle. And we have already made this observation in our few examples we have solved previously, but now we have done it in detailed mathematical steps. How is that having the unit circle inside the ROC will guarantee the system stability? Okay, now for an LTI system to be both causal and stable, so what would happen, or what are the conditions in order to have a system that is both causal and stable? Let's move to our whiteboard and see how it goes. So this is a Z domain, and this is a unit circle, and now we have learned that for the system to be causal, the ROC has to be going outward, and for the system to be stable, the ROC must include the unit circle. Let's assume we have a system whose pool is located over here. This is our pool. For this system to be, of course, the ROC in this case, we would draw a circle going like this. The radius would be equal to the pool value, and the ROC could be either going outward like this one. In this case, the system would be causal, but it will not be stable because the ROC does not include the unit circle. But if we choose the region of convergence to be inside this circle like this, now the system will not be causal, it's anti-causal, but it will be stable because the unit circle belongs to the region of convergence. So what do you think would be the condition for the system to be both causal and stable? Let's take a look at this system. Assume this is a Z domain and this is a unit circle, and let's assume that the pools we have is here. So now the region of convergence would be, we will take the outermost pool and draw a circle like this one, and the ROC would be either going outward, right? In this case, the system would be causal because the ROC is going outward and the sequence in time is right-sided, and also it will be stable because the unit circle belongs to the region of convergence. So it looks like that the condition for the system to be both causal and stable is that we should have all the system pools located inside the unit circle. This will guarantee an ROC going outward, which includes the unit circle. In other words, a causal and stable system. So for an LTI system with a rational function h of z to be both causal and stable, all pools of h of z must be inside the unit circle, and its region of convergence should be going outward from the outermost pole, as we have seen on the whiteboard. This is a condition for causality and stability. Okay, so now the equivalent system functions of an LTI system. Let's say we have two systems like this put in parallel. X of n goes to h1 of z and h2 of z. This is equivalent to adding h1 of z plus h2 of z. It's simply because now you have x of n will be convolved with h1 of n, or equivalently x of z multiplied by h1 of z plus x of z multiplied by h2 of z. So if you take x of z common factor, you will get h1 of z plus h2 of z. Here, these systems are cascaded, h1 of z followed by h2 of z. It's equivalent to multiplying them together, because you will have x of z multiplied by h1 of z, and this output, which is x of z times h1 of z, will be multiplied with h2 of z. So now this is equivalent to multiplying h1 and h2 of z. Okay, so there is a family of LTI systems that describe what's called the linear constant coefficient difference equation, and we have discussed this equation in the introduction we had in this course. This equation simply is that y of n, the output of the system, equals to two summations. The first summation is y of n minus k, the previous outputs. If you put k equals to 1, this would be a1 y of n minus 1, the previous output. a2 times yn minus 2 is the output before, a3 times yn minus 3 is the output before that, and so on. So this term over here represents the dependence on the previous output. And this summation over here represents the present and previous inputs. K equals to 0 will give you b naught x of n, which is the present input, and then b1 x of n minus 1, the previous input, b2 x of n minus 2 is the input before that, and so on. So this equation is simply saying that the present value of the output is a linear combination of previous outputs and present and previous inputs. This is a linear constant coefficient difference equation. It's called linear because there is no signal multiplied by another signal, no x times y or x times x, only constants ak times y and bk times x, and that's why it's called constant coefficient difference equation. And always we assume that x of n and yn equals 0 for n less than 0, that is, the system was initially at rest. So let's apply Z transform to this equation and see how it goes. If you remember in the introduction we had, in the chapter 1, in the introduction, chapter of introduction, we tried to solve a system that had a dependence on the previous output and find the impulse response, and it was kind of tricky, and also it was tricky to check its stability. But right now we have a tool which is Z transform, and this tool will help us to deal with such a system. Applying Z transform to this system, we will get y. Let me do it on the whiteboard instead. So we had in the equation y of n equals summation ak y of n minus k plus another summation bk x of n minus k. So applying Z transform over here, this would be y of z equals 2. Now Z transform is a linear transform, so we can find Z transform of this term and then this term and add them together. This term is a summation, so we can find the Z transform of the terms inside the summation and then we add them. Now we're using the Z transform linearity property, so summation of ak, and now we can use time shift property. Y of n minus k is a shifted signal in time, and the transform would be z to the minus k times y of z. Similarly, here we would have the summation bk, and here x of n minus k, we'll apply the time shift property. It will give us z to the minus k x of z. Now this summation is over variable k going from 1 to n, and this summation is on variable k going from 0 to m. So now y of z does not depend on k, so we can move it out of the summation. Same for x of z, we can move it out of the summation because it does not depend on k. So moving y of z outside the summation and moving x of z outside the summation, we will get this. We will get y of z equal to y of z times summation ak z minus k from k going from 1 to n plus x of z times the summation k going from 0 to m bk z to the minus k. And now we can move this whole term to the other side. So we can take y of z common factor, and you will have 1 minus the summation. Of course, if you go back to the original equation we had here, there is a negative sign over here. As a matter of fact, some textbooks shows this negative sign, some other textbooks just removes it. It doesn't really matter because we can have it like this, or we can even hide it inside ak and find a new constant ak that's equal to minus this constant. So it does not really matter. So going back to our whiteboard, I have to add this negative sign in order to be consistent with the notation in the slide. But again, some textbooks have it, some textbooks does not. It doesn't really matter. So we'll have this negative sign over here. This will give us a negative sign over here. And moving to the next slide, we will have a negative sign over here beside this y of z. That's why we can move this entire term, we can move this entire term to the other side, and we take y of z common factor. So we will have y of z times 1 plus this summation. So moving back to our slide, here we go. So we have y of z times 1 plus summation from k equals 1 to n ak z to the minus k equals x of z times the summation k from 0 to m bk z minus k. And if you take a look at this equation, this summation actually, if you expand it, it's b0 plus b1 z minus 1 plus b2 z minus 2 plus b3 z minus 3. It's a polynomial in z minus 1, polynomial of degree m. And this term is 1 plus, and if you expand this summation, it's a1 z minus 1 plus a2 z minus 2 plus a3 z minus 3. It's another polynomial in z minus 1. So combining this with what we have learned before, that h of z, the system transfer function, is y of z over x of z. Now y of z over x of z would be this polynomial over this polynomial. Since h of z equals y of z over x of z, now h of z would be a ratio between two polynomials. The polynomial in the numerator is of order m, and the polynomial in the denominator is of order n, and now we have a rational function, i.e. a ratio between two polynomials. And now we can use what we have learned in the inverse Z transform during long division and or partial fractions in order to find h of n, the system's impulse response. Example, let's say we have an LTI system which has the following system function. H of Z equals this polynomial over this polynomial, and we need to find the system's LCDE, the linear constant coefficient difference equation. So let's move to our whiteboard over here. So H of Z is equal to this polynomial over this polynomial. And we need to find the linear constant coefficient difference equation describing this system. So basically we know that h of z is equal to y of z over x of z. So this rational function should be equal to y of z over x of z. So in order to find the LCCDE, actually we will multiply this numerator with x of z and this denominator with y of z, and then we have our LCCDE. So this is how it goes. We will be having this polynomial in the numerator multiplied by x of z. It will be equal to the polynomial in the denominator times y of z. And now we can do the inverse z transform. So 6 times x of z, the inverse would be 6x of n. Let me do it over here. So now when you multiply 6 times x of z and doing the inverse, you will get 6x of n. And then we have minus 10 z minus 1 x of z. So minus 10. Z minus 1 x of z, now we have a time shift property. This will give us x of n minus 1. Plus 2z minus 2 times x of z will give us 2x of n minus 2. Okay, and now we have the first part of the LCCD. This will be equal to 1 times y of z. This will give us y of n minus 3 z minus 1 y of z. This will give us y of n minus 1. So now we get the idea, and this will be plus. Now we have 2z minus 2, so 2 times y of n minus 2. So now we have our LCCDE. This is the equation we are looking for. Now we can write it in a more clear form, which is usually y of n equals 2. So we will move all these terms to the other side of the equation. So now h of z is y over x, and now we can multiply the polynomial in the numerator with x of z and the polynomial in the denominator with y of z, like this one, and then we can do the inverse, and this would be the difference equation. Now what if I asked you to find the impulse response? How can you find the impulse response of this system? If I ask you to find the impulse response, basically what you need to do is to find the inverse z transform of this h of z. Now it's an improper rational function, so first you would do long division and then partial fraction, and then you can find the h of n. Now if you click this hyperlink over here, actually it was on one of the examples we have solved previously when we were working on the inverse z transform, and now it's improper rational function, long division. We have already done this example before, and we can find h of n. So this is actually a typical question in the exam, where I'll give you a transfer function. I would ask you to find the LCCDE, find the impulse response, maybe find the pools and the zeros, determine the causality and stability, and maybe I will ask you to draw a block diagram of the system. What about the block diagram? What if we ask to draw a block diagram of the system? So let's see how can we draw a block diagram of this system. Basically, the equation was like this: 6x of n minus 10 x of n minus 1 plus 2 x of n minus 2. This was the first part of the equation. So now we have x of n, and this block over here is a multiplication with a constant, so we multiply x of n by 6, and then this block will give you a delay of one sample, will give you x of n minus 1, which is then multiplied by minus 10, added with 6 times x of n, and both of them will be added to 2 times x of n minus 2. If you go back here, this is actually the first part of the equation: 6 x of n minus 10 x of n minus 1 plus 2 x of n minus 2. And this basically will be added to 3y n minus 1 minus 2y n minus 2 to give you y of n. So now we will have, this is y of n, have a delay and feedback. This is basically the feedback part. We will get y of n minus 1 multiplied by 3, y of n minus 2 multiplied by minus 2, and add them to whatever is coming from the upper part. Now, this part is the feed-forward part of the system, and this part is a feedback part, where you take the output, feed it back into the system to compute the present value of the output. Now, again, this completes a typical question in the exam. I will give you a transfer function, or an LCCDE, or a block diagram. From any one of these, you can find the other. If I give you this block diagram, you can find LCCDE, from which you can find h of z, from which you can find the impulse response, from which you can find the pools, zeros, commenting causality and stability, and then you can compute the output for any given input. So usually this will be the question you're going to see in the exam. Okay, so slides 72 and 73 are basically saying that the LCCDE we have will give us a rational function. In the numerator we have a polynomial of degree m, and hence we have m zeros, and in the denominator we have a polynomial of degree n, and hence we have n pools. And let's skip the equations in these two slides. The concept is having a rational function of order m over order n. In the numerator, order m means m zeros, and in the denominator, order n means n pools. So let's skip this slide as well and going to this slide. So now if we have a zero, which takes the form 1 minus zk times z minus 1, where zk is the location of the zero. Now we would have a 0 at z equals zk, and we'll have a pool at 0. How's that? If you put z equals to 0 in here, 1 over 0 give you infinity. Infinity in the numerator means we have a pool. So every 0 at any location will come with a pool located at the origin. Similarly, if we have a pool 1 minus p kz minus 1, this will give a pool at z equals pk, and a 0 and z equals 0. How's that? If you put z equal to 0 over here, 1 over 0 is infinity, but this infinity is happening now in the denominator, which will give us a 0. So every pool at any location will give you a 0 at origin. So as you can see, we have many pools at origin and many zeros at origin. That's why pools and zeros at origin are not counted, because every 0 will come with a pool at origin, and every pool will come with a 0 at origin. Okay, so now if we have a rational function with distinct pools, so basically distinct pools mean pools that are different, there are no repeated pools. This would be the form we have. H of z is a summation bkz minus k over 1 plus summation akz minus k, and by the way, bk are called the feed-forward coefficient and ak are called the feedback coefficient, so we will get this rational function ratio between two polynomials. And in order to do the inverse Z transform, first we will ask ourselves a question: is this a proper rational function? If m is less than n, so it's a proper rational function and we can do a partial fraction right away. But if m is larger than or equal to n, we have to do long division first and then we do partial fraction. So doing the long division will give us terms like 1 and z minus 1 and z minus 2. So in this case, h of z will have summation of terms of the form z minus k, so z to the power 0, z to the power minus 1, minus 2, with coefficients ck, and then you can get a proper rational function, and then do partial fraction and get constant over 1 minus pool pk times z minus 1. So this is a general form of the partial fraction expansion. And let me go back to one example we have seen in order to clarify things. So if you go to this example, now this is an improper rational function. Doing the long division will give you this kind of term. This 1 over here is basically z to the power 0. And if the order of the polynomial in the numerator was 3, we will get another term z minus 1. So doing the long division, we will get terms of the form z to the power minus k. Here it's just z to the power 0, but it can be also plus z to the power minus 1 plus z to the power minus 2. And now we will get a proper rational function which can be done using partial fraction, and the general term would be z to the minus k, z to the minus z, z to the power 0 plus z to the power minus 1 minus 2 plus the terms we get from the partial fraction constant over 1 minus 2 z minus 1. So let me go back to the general expression we had over here. So now this summation corresponds to the result of the long division, and this summation corresponds to the partial fraction. And now we can simply do the inverse Z transform. How is that? This kind of term corresponds to a time domain sequence pk to the power n times u of n, if it's a right-sided sequence. And this kind of term corresponds to delta of n minus k. So doing the long division and then the partial fraction, we can do simply the inverse Z transform. These slides are summarizing what we have already learned. So don't get yourself confused over here. We're trying to summarize what we have learned and put it maybe in a more formal terms. So now, if we have this kind of rational function, we will do long division, partial fraction. The long division part will give us this term, and the partial fraction part will give us this term. And just be ready to do it in an actual example, like the examples we have been doing before. Don't confuse yourself with this kind of general equations over here. And the purpose of this general equation is simply that in MATLAB we have a command which will give us AK, PK, CK, and will do the partial fraction and long division for us. That's why I needed to define these kind of terms. Okay, forget about how to compute AK. We already know how to compute the constants AK. And in MATLAB, we have a command that's called residue Z. Residue Z will give us three outputs, A, P, and C. The A are the constants over here, P are the pool location, and C are the constants we're going to get from the long division. And you give residue Z two inputs, B and A. B is the feed-forward coefficient, A is the feedback coefficient. So let's try to open MATLAB together and try this command. So let's consider the example we had before. This example, h of z is this polynomial over this polynomial. Now we need first to identify the polynomials for the feed-forward and the feedback, the feed-forward coefficient and the feedback coefficient. The feed-forward coefficients are 6 and minus 10 and 2 in the numerator over here. These are the b's. And the A's, the feedback coefficient, are 1 and minus 3 and 2. Why is that? If you go back to the LCCDE we had, the general form of h of z, bk are the numerator coefficients and ak are the denominator coefficient. So now b would be 6 and minus 10 and 2, and a would be 1 and minus 3 and 2. So if we go to MATLAB, here I have defined two vectors, b equals 6 and minus 10 and 2, and a equals 1 and minus 3 and 2. And now I'm using the command residue z, and I will give it the two variables b and a, and expecting three outputs: a capital, which is the constants associated with a partial fraction; p is the location of the pools; and c is the result of the long division. So now the result of the long division is 1, and we have two pools located at 1 and 2, and the constant corresponding to the pool 1 is 2, and the constant corresponding to the pool 2 is 3. What is this supposed to mean? If we go back to our example over here, the result of the long division is 1, which comes in MATLAB as a variable c. And here we have two pools, 2 and 1, which is the vector p, which have two pools, 1 and 2. And the constant associated with the pool 1 is 2, which is basically here the term with the pool 1 has a constant b, which is equal to 2. And the pool 2 has a constant equal to 3, which is this pool 2 has a constant equal to 3. So the command residue z can actually be used to do the long division and the partial fraction. So you can use it actually to solve or to double check all of your solutions when it comes to computing the partial fraction and long division. Okay. So now if h of z has distinct pools, non-repeated pools, now the impulse response will be like this. The terms of the form z minus 1 will be in time domain corresponding to terms delta of n minus k, which is this kind of term, delta of n minus k. And the fractions we have over here will give us pk to the power n u of n, which is this kind of term. So now we can get a general form for the impulse response. And now in MATLAB also, since you have ak and pk and ck from the command residue z, you can write h of n right away in MATLAB and get the waveform how it would look like. Okay, so system classification. The systems can be classified based on the length of the impulse response. In this part, we're trying to summarize things we are trying to wrap up things we have already learned during this chapter. So you will find some things that are being repeated to wrap things up, to remind you of what we have learned so far and to finalize this chapter, hopefully. So, infinite impulse response system, or IIR systems, are systems that has feedback. Having feedback will result in having pools, and these pools will give you in time domain a term of the form p to the power n u of n. Hence, the impulse response will have infinite duration. So, a system with feedback will have a pool, and this pool will give us a term p to the power n u of n, and then the impulse response will have an infinite duration. On the other hand, if there is no feedback, there will be no pools, and hence it will be a feed-forward system, in which case h of z will be just the numerator polynomial, summation bk z minus k. And hence the impulse response will be simply some shifted impulse. Z minus k will give you delta of n minus k. We can also classify systems based on having feedback. Recursive systems have feedback. Recursive systems are systems whose output is fed back into the system. And in this case, having feedback will result in having pools. And pools will give us an impulse response with the term pool to the power ku of n, which is an infinite impulse response system. So recursive systems in general are infinite impulse response systems. Non-recursive systems, on the other hand, does not have any feedback. And hence it does not have any pools. That's why it's kind of an FIR system, finite impulse response system. And of course, as we have seen before, finite impulse response systems are always stable because they do not have any pools. Because basically, the stability requires that the region of convergence includes the unit circle. So if you do not have any pools in FIR systems, you would be having an ROC that extends over the entire Z domain, possibly except Z equals 0 or so. So for an FIR system, you will always be having the unit circle as part of the ROC, and the system will always be stable. Or also we can look at it from a different point of view, where the impulse response is finite. In an FIR system, the impulse response is of finite duration. So applying the definition in which you sum the absolute value of h of n, you will always get a finite value. That's why FIR systems are always stable, as opposed to IIR systems, systems with infinite impulse response, which might be stable or might not be stable. The third classification is based on pools and zeros. An all-zero system is a system that have all zeros and does not have any pools. If it does not have any pools, this means there is no feedback, i.e. the feedback coefficient AK is equal to 0, and hence it will be an FIR system. An all-pool system, on the other hand, is a system that have no zero. It would have all pools but no zeros. And in this case, having pools means it's an IIR system, an infinite impulse response system. So, example, let's say we have this h of z. It's a ratio between two polynomials. The polynomial in the numerator is of order 2, polynomial in the denominator is of order 3. So, this system will be having how many zeros? Since the numerator is of order 2, then we will be having 2 zeros. And since the denominator is of order 3, now we'll be having 3 pools, and we will call it a third order system. The number of pools will determine the order of the system. This is a third order system because it has 3 pools. Since we have feedback, since we have this feedback polynomial over here, the denominator is the feedback part. It's a recursive system. It's an IIR system. Okay, so, and in MATLAB, we can actually use some of the commands we have learned in order to check the system, find the pools, find the zeros, and so on. So in MATLAB, let's define two vectors. Vector B that will contain the feed-forward coefficients, which are 1 and 0 and minus 1. Why do we have this 0 over here? It corresponds to the z to the power minus 1. So as if we have 1 minus 0 times z minus 1 minus 1 times z minus 2. So now we have to have this 0 over here to account for z minus 1. And a would be the polynomial of the denominator over here, 1.9.6.05. This is the denominator we have over here. This is the feedback coefficient. Okay, let's say we want to find the pools and zeros. Pools are basically the roots of the denominator polynomial. This polynomial, we need to factorize this polynomial and find its roots. In MATLAB, there is a command called roots that will give us the roots of a polynomial. So roots of a, the feedback polynomial, or the polynomial in the denominator, will give us the pools. Let's try it in MATLAB. So pools equal to roots of a. So now we have 3 pools, and one of them is real valued and the other 2 are complex conjugate pools. And as expected, because it's a third order polynomial, now we have 3 pools. If you want to get the zeros, zeros are basically the roots of the feed-forward polynomial, or the polynomial in the numerator, which is b. So now we have 2 zeros at 1 and at minus 1. There is a command in MATLAB that's called Z-plane. Z-plane actually will draw Z-plane, the unit circle, and will locate the poles and the zeros on the Z domain. So let's try and see how it goes. So now if we write Z-plane of B and A, the feed forward and feedback polynomials, you will get this curve. Let me try to expand it. So this is the unit circle, and now we have two zeros at 1 and -1. So now this is a 0 at 1, as you can see it's a circle at 1, and another 0 at -1. And now we have three pools. One of them is at -0.09, which is this pool. And we have two other pools which are complex conjugate to each other, this one and this one. So as you can see, the command Z-plane will give us the Z-plane with the unit circle and will put the pools and zeros on top of it. As you can see here, we have a 0 at origin. As we said before, every pool comes with a 0 at origin, and every 0 comes with a pool at origin. So 3 zeros at origin and 2 pools at origin. 2 will cancel out with 2, will have 1 0 at origin. Looking at the output of this command, Z-plane, now we can see that this system can be both causal and stable because the three pools we have are located inside the unit circle. So choosing the ROC to be going outward outside of the outermost pool, which is this one, or these two actually, now we can have a system which is causal and stable. In MATLAB also we have a command that's called impz. It will give us the impulse response of a system given its polynomials, feed forward and feedback polynomials B and A. And of course in this case this system is an infinite impulse response because it has feedback. So the impulse response would be of an infinite duration. That's why we add this length over here. We're asking MATLAB to draw the first 100 samples of this impulse response. Let's go back here and try to see how it goes. Imp Z B A and 100 samples. So now we will be having our impulse response. As you can see over here, it's not that clear, so maybe we can do a different thing. We can say H equals to imp Z B and A and 100. This will give you the first 100 samples and put them in the variable H. Now we can plot H and let's take a look. Now this is the impulse response we have over here. So again, MATLAB is a very useful tool in this case to get the impulse response and see how it looks like. And also in MATLAB we have a command that's called filter. Basically, any discrete time system of this form can be thought of as a digital filter. And now we want to apply a certain input X to this filter in order to get the output Y. So let's assume for this system we have an input X of n, let's say of few samples, 1, 0, 1, 1, any kind of input, and we want to find the output. So let's go to MATLAB and let's define X to be, let's say, equal to 1, 2, 3, 4, and 5, any kind of input. And then the output would be, we'll use the command filter, and we will give it B and A and the input X. And this would be the corresponding output, which is basically the convolution of the impulse response of a system with this input. And so basically the command filter would apply the input X to this system and get us the output, the corresponding output Y. As we've been saying, any discrete time system of this form can be considered as a filter. That's why by the end of this course, hopefully, when we talk about the filter design, digital filter design, FIR and IIR, it's basically all about this kind of system. What kind of feed forward coefficient we have, what kind of feedback coefficients we have, what is the order of the system, where is the location of pools and zeros in order to achieve a low pass filter or a high pass filter or of this characteristic and so on. So the filter design is basically about translating what kind of requirements or filter specification we have into getting a discrete time system with this kind of pool, with this kind of zero, with this kind of polynomials. This will give us the required frequency response. Okay. And this is an example we have been talking about right now. This is the output of the Z plane command, which will give you the Z domain with the unit circle and the pools and zeros. Let me skip this part for now. So slide 84, 85, and 86, maybe up to 87. Let me skip this part for now. So this basically will conclude the Z transform chapter. We will ignore the slides from 84 up to the end. And now we have completed the Z transform chapter, and now we are ready to move on next week, hopefully, to the next chapter, which will be the design of digital filters.